So keeping those two things from the last video in mind, I want to walk through a couple of conceptual examples to try to help us understand how membrane potential is created. I want to give you a minute to consider the situation that I've painstakingly created here with hours of my life making this slide. We have positive and negatively charged ions that are separated by a membrane that's impermeable to those ions. So here I want you to ask yourself if there's a concentration gradient for the ions. If so, what is it? Because remember, we can calculate it. Which ions are permeable? And lastly, what is this picture going to look like when I press the start button? In other words, what happens if I let it go until it reaches a steady state? It would be really helpful for both of us if you could indulge me by pressing the pause button on this recording to give yourself time to actually think about the answers to those questions. So go ahead and do that. Okay, so hopefully you didn't cheat. So in this case, we actually do have a concentration gradient because we have 1 positive charge outside the cell and we have 7 positive charges inside the cell. So there's a gradient of 6 for positive charges. The same is true for the negative charges. There's 1 outside and 7 inside. So this gives us a gradient of 6. Now in this example, there is no permeability. And so that means despite the gradient, no movement of ions can occur. So this doesn't reflect the situation inside of our body, but it is a really important example because as things get more complicated later, people tend to forget about the basics. Without permeability, membrane potential cannot exist because ions can't move. Here's the second example where we've introduced a non-selective ion channel. Now we start off with the same initial conditions as the last example, but I want you to again take a minute to answer those same questions. Is there permeability? If so, to what? Is there a gradient? If so, what is it? And what is this going to look like when I press the start button and let this move into a steady state? So in this example, we again have a gradient of 6 for both positive and negative charges. And this means that ions are going to want to move down that concentration gradient from higher concentration to lower concentration. After that happens, the cell should look something like this, with 4 positive charges inside and outside the cell, and 4 negative charges inside and outside the cell. The movement of 3 positive and 3 negative charges out of the cell follows the rules of diffusion to make this happen. Remember, diffusion says that ions will move from high concentration to low concentration as long as the concentration gradient exists. When we have 4 and 4, it doesn't. But do we have membrane potential? If we think about the extracellular environment at this point, then you can see that we have 4 positive and 4 negative charges out there. So that means that the net charge in the extracellular environment is 0. Inside the cell, we also have 4 positive and 4 negative charges, so the net charge there is 0 too. Thinking back about what we said about electrophysiology in the first part of this unit, if we don't have any difference in charge across the membrane, then the membrane potential is 0. So from this example, we can really see the importance of selective permeability. If we had freely permeable membranes and ions could just move down their concentration gradients entirely, we would eventually end up with equal concentrations of those ions on both sides of the membrane. Everything would be completely balanced, and that means that membrane potential wouldn't exist, and excitable tissues like nerves and muscle wouldn't be able to function properly. So this situation doesn't exist inside the body pretty much unless you're dead. So finally, we'll get to our third example, which is what's actually happening inside of neurons and inside of muscle tissue. So again, same initial conditions, but now we have selective permeability because this ion channel is only selective for positive charges. So again, is there a concentration gradient? Is there permeability? What does this look like when it reaches the steady state? And do we have membrane potential? So again, go ahead and press the pause button, take a minute to think about this, no cheating. So based upon what we just talked about in example 2, the first thing we would expect to see happen here is for ions to move down their concentration gradients. So because the concentration of positive charges is higher inside the cell than outside, we would expect to see positive charges moving out to follow the rules of diffusion. So that means that we should see something that looks like this. Remember, only positive charges can move because that's the only thing we're permeable to. But now let's consider the charge environment. So at this point, we have 4 positive charges outside the cell and 1 negative charge out there. So that means that we have a net of +3. We have 4 positive charges inside the cell and 7 negative charges in there. So that's a net of -3. In this situation, we actually have a difference in charge between the inside and the outside of the cell. So this means that now those attractive forces between charged particles are going to kick in, and they'll influence the movement of these charged ions. Remember, opposite charges attract. So essentially what's going to happen is that some of those positive charges that are outside are going to get pulled back into the cell because of the electrostatic attraction. Again, opposite charges attract. And so what we're really going to end up with is a steady state that looks something like this. You'll notice that we still have a concentration gradient, and if you add up the charges, you'll also see that we still have a difference in charge across the membrane. That's normal, it's desirable, and that's the situation that's inside of our bodies. Now, one thing to point out is that the repulsive forces acting on the negative charges are attempting to push them away from the negatively charged intracellular environment. And similarly, there's electrostatic attraction between the negative charges inside the cell and the positive charges that are outside. Sometimes people get confused because they wonder in this example why the positive charges are moving back in instead of the negative charges moving out. The reason for that is because of permeability. The ion channel in this example is only permeable to positive charge. So even though those forces exist and are acting on the negative charges too, the negative charges are physically unable to move across the membrane. So what you can hopefully see from this example is that there are 2 or 3 intersecting forces that set membrane potential. The first is concentration gradient pushing ions towards chemical equilibrium. And the second is electrical potential pushing ions towards electrostatic equilibrium. When those 2 forces balance each other, equal and opposite, what we end up with is membrane potential, the potential energy to do work. So I have 2 more examples here for you to practice with. Again, keeping in mind that these are just conceptual examples at this point to get you comfortable with the idea of concentration gradient and the idea of electrostatic potential. So for each of these, I want you to answer those same questions that we went through in the last examples on your own.